Okay, we can see the slides, so please start.
So thank you. Today we will talk about online learning of logic-based neural network structures. So in this work, we propose two structural learning algorithms to learn logic theories based on neurology. So the agenda for today is I will give a brief introduction of the work, some background knowledge, show our proposed structural algorithms, some experiments, and finally conclude. So to start, like I said, we'll present two structural learning algorithms for neurolog. The first one is based on online structural learning by revision, OSLR, and the other one is based on Meta-Interpretive Learning. So what's neurolog? Neurolog is a first-order logic language that takes as input logic theory, a first-order logic theory, and transforms this into a neural network and perform the inference based on the inference of this neural network. It's done so by transforming the knowledge facts into matrix representation, and the rules are represented as mathematical operations on those matrices. So talking a little bit about online structural learning by revision, it is an algorithm that learns first-order logic based on theory revision. It can start from an initial theory, or it can start from an empty theory. Then it represents theory in a tree structure like we're showing here in this slide. Here we have a theory of three rules. All of the rules start with the same predicate in the head, and they are represented by a single theory, as a single tree. If there were more predicates, if there were rules with different predicates in the head, there will be a tree for each predicate appearing in the head of the rule. So this structure has two functions. First, represent the rules and point out the revision points in the theory. And the second one is to group the examples of the training base. So when an example arrives, it's passed by the theory from the root of the tree, and we try to infer the example with partial rules, and if we can infer the example of the rule, the example goes down to the path of the rule until it reaches a leaf. If at a certain point we can no longer infer this example, it goes to a false leaf that will accommodate all the examples that cannot be proved by this part of the theory. Then these examples are used in the revision process. So here in the original OSLR, we have two ways of revise the theory. One, we can remove a leaf from this tree in order to remove this literal, or we can remove an entire row of this tree. And the second way is by adding nodes to the tree by extending a row or to generate new rules. So the first algorithm we propose here is to adapt OSLR directly to neurolog. And then we have our second algorithms that use the Meta-Interpretive Learning. Here we use the same mechanism of OSLR for theory revision, but instead of using its original operators that add new nodes to the tree based on the bottom clause, instead of using the bottom clause here, we use a new theory that is a higher order theory that serves as a template to propose new literals to be added to the tree. So here the user can find a set of meta rules, of higher order rules, that will be used to generate first-order rules to be added to the tree, use the same underlying mechanism of OSLR. Due to the short time, I cannot give much detail on this mechanism, but it will, based on the revision points, will propose a revision, and then if this revision is approved, it's based in some criteria, it's implemented in the theory. So we performed some experiments of these systems on 3 datasets: the Costa, UMLS, and the UWCSE datasets. So these are all batch datasets. So in order to retrieve the online, or in order to test the online learning algorithm, we have to simulate online environment. And we did it by splitting the examples into iterations, and at each time we pass a batch of examples to the learning algorithm that will look at these examples and adjust its model based on it. And then the model will be tested in the next examples before using it to train the model. So it's a sequential approach to evaluate this model. So as we can see here, our proposed algorithms are doing well in 2 of the 4 relations of the Costa, which are the semi-alpha and semi-venue. So here the Meta-Interpretive Learning approach is doing better, and here as well. And the others, they are, for the same baby, they are not very good, but for the same title, the Meta-Interpretive Learning has a stable performance above the other systems. Finally, in the remaining data sets, we show that both of our algorithms are doing well on the UMLS dataset, but cannot perform very well on the UWCSE dataset. Although when we started from some initial theory, we can have results similar to the theory. I believe this concludes. To summarize, we present 2 structured learning algorithms based on Neurolog. We compare our approach or proposal with the original OSLR and the RDN boost. Yes, future work would like to experiment Neurolog learning algorithms on datasets mixing the relational part of neural networks with propositional neural network models, which is a benefit of Neurolog that can combine both relational parts of neural networks described through first-order theory with traditional neural network approach. So, thank you. If you have any questions.